Welcome to this walkthrough of LeetCode problem number 112, path sum. In this problem, we'll explore how to determine whether a binary tree has a root-to-leaf path with a given target sum. Stay tuned as we dive into the details and discuss different approaches to solve this problem effectively. In this problem, you're tasked with determining whether there exists a root-to-leaf path in a binary tree where the sum of the node values along that path equals a given target value, called target sum. A root-to-leaf path means we start at the root node of the tree and traverse down to a leaf node, which is a node without any children. The input consists of two elements: the root of the binary tree, which is represented as a tree node object containing integer values, and the target sum, which is a single integer. The output is a Boolean value, true if such a path exists, and false otherwise. Here's an example to illustrate the problem. Suppose the input binary tree is structured like this. The root node has a value of 5, with two child nodes 4 and 8. From node 4, we have a left child 11, which itself has two children, 7 and 2. On the right side of the tree, node 8 has two children, 13 and 4, and this last node 4 has a right child 1. Along one possible root-to-leaf path, we traverse 5, 4, 11, and 2. If we add these values together, the sum is 22, which matches the target sum. Therefore, the output for this example is true. Now let's look at another example. This time, the tree has a root node with a value of 1 and 2 children, 2 and 3. The target sum is 5. The possible root-to-leaf paths are 1 to 2, which sums to 3, and 1 to 3, which sums to 4. Neither of these paths adds up to the target sum of 5. So, in this case, the output is false, as there's no root-to-leaf path that meets the required sum. In a third example, the input tree is empty, meaning there are no nodes at all, and the target sum is 0. Since the tree has no root or leaf nodes, there are no paths to consider, and the output is false. This example highlights how the problem handles an edge case where the tree is entirely empty. Finally, let's discuss some important edge cases and constraints for this problem. First, if the tree is empty, the output should always be false since there are no paths. For a single node tree, the solution should check if the node value equals the target sum. If it does, return true, otherwise false. The solution must also handle negative values, both in the node values and the target sum. Additionally, there may be cases with multiple paths in the tree, but only one of them matches the target sum. Lastly, the solution needs to work efficiently for larger trees, with up to 5,000 nodes, ensuring it can handle input sizes at the upper limit without performance issues. To solve the path sum problem, we can consider multiple approaches, each with its own trade-offs. The first approach is the brute force method, where we generate all possible root-to-leaf paths in the binary tree. The idea here is to recursively traverse the tree, keeping track of the current path, and then calculate the sum of each path to check if it matches the target sum. While this method ensures that no potential solution is missed, it is computationally expensive. The time complexity is O(n) for the traversal, but since we store all paths, the space complexity can grow to O(h*(n), where h is the height of the tree. Additionally, this approach is inefficient because it computes all paths unnecessarily, even when we might find a valid solution early on. A more refined option is the recursive depth-first search, or DFS. Here, instead of generating all paths, we directly calculate a running sum as we traverse from the root to the leaves. At each step, we subtract the node's value from the target sum. If we reach a leaf node and the updated target sum equals 0, we know we've found a valid path. This method is more direct and avoids the overhead of storing paths, making it a significant improvement over the brute force approach. The recursive DFS approach has a time complexity of O(n), as we visit each node exactly once. The space complexity, however, is O(h), which comes from the recursive call stack and depends on the height of the tree. While efficient, it does have a drawback: deep trees can cause stack overflow due to the recursion. To address this, we can use an iterative DFS approach, which eliminates recursion by using an explicit stack. Here, we track the current node and its running sum iteratively. We start with a stack containing the root node and its value. Then, we process each node by popping it from the stack, updating the sum, and pushing its children back with their respective sums. If we encounter a leaf node where the current sum equals the target sum, we return true. Like recursive DFS, the time complexity remains O(n), and the space complexity is O, H, but this method avoids the risks associated with recursion. Another alternative is breadth-first search, or BFS, which processes nodes level by level using a queue. In BFS, we enqueue the root node with its value as the initial sum, then explore its children while updating the sums. This approach is particularly useful for balanced trees but may be slower for unbalanced ones, as it explores all nodes at a given depth before moving deeper. The time complexity is O, N, and the space complexity depends on the maximum width of the tree, O, W. However, for deeply unbalanced trees, BFS might explore more nodes than necessary compared to DFS. The recursive DFS approach is chosen as the optimal strategy for this problem for several reasons. First, it is efficient, directly calculating the running sum without unnecessary computation. Second, it is simple and intuitive to implement, aligning well with the hierarchical structure of binary trees. This simplicity makes it particularly suited for coding interviews. A key insight in this approach is that we don't need to track entire paths, we only need to maintain the running sum at each step. This realization simplifies the problem, reducing it to progressively subtracting from the target sum until we reach a leaf node. Recursion naturally fits the binary tree structure, avoiding extra data structures like stacks or queues. However, it's important to acknowledge the trade-offs. Recursive DFS is clean and concise but can lead to stack overflow for extremely deep trees. In contrast, iterative DFS avoids recursion but introduces additional code complexity. BFS, while effective for level-order traversal, may not perform as well on unbalanced trees due to unnecessary exploration. Overall, recursive DFS strikes the best balance between simplicity and efficiency, making it the most practical choice for this problem, especially in interview settings where clarity and directness are valued. The problem path sum asks us to determine if there is a root-to-leaf path in a binary tree where the sum of the node values along that path equals a specified target sum. Each node in the tree contains an integer value. To solve this, we'll use depth-first search, or DFS, which is a recursive approach to explore all potential paths from the root to the leaf nodes. Let's break down the algorithm. First, we need to handle the case where the tree is empty. If there's no root node, it means there are no paths to check, so we simply return false. Next, we address the base case for leaf nodes. If the current node is a leaf, meaning it has no left or right children, we check if the remaining target sum equals the value of the current node. This is because a leaf node marks the end of a root-to-leaf path, so we can directly validate whether the path sum matches the target at that point. For non-leaf nodes, we proceed with recursive traversal. We subtract the current node's value from the target sum to reflect the remaining sum needed for the path. Then, we recursively check both the left and right subtrees, passing the updated target sum and the child nodes into the recursive calls. The results for the left and right subtrees are combined using a logical OR operator. This means that if either subtree contains a valid path, we return true. Finally, if no valid path is found after exploring all possibilities, we return false. Key insights for this approach include the suitability of DFS for exploring all root-to-leaf paths and the simplicity achieved by reducing the target sum at each step. By subtracting the current node's value, we avoid the need for additional data structures to track the path sums. Detecting leaf nodes is another critical aspect since only these nodes can define valid root-to-leaf paths. The binary tree structure itself provides the framework for our traversal, while recursion ensures we can efficiently backtrack as needed. The recursion relies on the call stack to keep track of the current path and to backtrack when necessary. In terms of complexity, the time complexity is O, N, where N is the number of nodes in the tree. This is because we visit each node exactly once during the DFS traversal. The space complexity depends on the height of the tree, which determines the maximum depth of the recursive call stack. For a balanced tree, the height is O log n, resulting in O log n space complexity. However, for a skew tree, the height can be as large as O n, leading to O n space complexity. There are also several edge cases to consider. For instance, the algorithm must handle an empty tree, where the output should be false. If the tree consists of only a single node, we check whether that node's value equals the target sum. Additionally, the algorithm must support trees with negative values, as they can influence the path sums. Finally, we ensure that the function correctly returns false when no valid path matches the target sum. To illustrate the algorithm, let's walk through an example with a specific binary tree structure. In our example, the binary tree has a root node with the value 5, and the target sum is 22. Starting at the root, we subtract 5 from the target sum, leaving 17. We then move to the left child, which has the value 4, and subtract it from the remaining sum, leaving 13. Next, we proceed to the left child of 4, which is 11, and subtract 11 to get a remaining target of 2. From here, we explore the left child of 11, which is 7. Subtracting 7 from 2 gives -5, which is not a match. So, we backtrack and check the right child of 11, which is 2. Subtracting 2 from the remaining target of 2 gives 0, which indicates we found a valid path. The path 5-4-11-2 sums to 22, so the algorithm returns true. This concludes our detailed breakdown of the algorithm and shows how it systematically explores all paths to determine whether a valid one exists. This solution implements the path sum problem using a recursive depth-first search (DFS) approach. Here's the detailed explanation of the code. 1. TreeNode class. The TreeNode class represents the structure of each node in the binary tree. Each node contains a value, val, a pointer to the left child, left, and a pointer to the right child, right. 2. Base case. The first check in the hasPathSum function is whether the current node, root, is none. If it is, we return false because no path exists in an empty subtree. 3. Leaf node check. We then check if the current node is a leaf node, i.e., it has no left or right children. For a leaf node, we return true if its value matches the remaining target sum, as this indicates a valid root to leaf path. For recursive DFS, if the current node is not a leaf, we calculate the remaining sum by subtracting the current node's value from the target sum. We then recursively call hasPathSum on the left and right subtrees, passing the updated remaining underscore sum as the new target. If either recursive call returns true, this indicates a valid path exists, and we return true. 5. Key insight. The algorithm ensures that each path is only evaluated once, making it efficient with a time complexity of O(n), where n is the number of nodes in the tree. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. This solution is concise and handles edge cases like an empty tree or paths that don't sum up to the target correctly. By leveraging recursion, the code efficiently traverses the tree and checks all possible root-to-leaf paths. Here, we begin by defining our TreeNode class, which represents the structure of a binary tree node. Each node has an integer value, val, and 2 child nodes, left and right. We also provide 2 constructors, one for initializing a node with just a value, and another for initializing a node with a value and its children. Then, we move on to the hasPathSum method, which determines if there exists a root-to-leaf path in the tree where the sum of the node values equals the given target sum. First, we handle the base case. If the root is null, the method immediately returns false since there's no path to evaluate. Next, we check if the current node is a leaf node, meaning both its left and right children are null. If it is a leaf, we compare its value to the target sum. If they are equal, we return true, indicating that the pathSum condition is met, otherwise, we return false. If the current node is not a leaf, we calculate the remaining sum by subtracting the value of the current node from the target sum. This gives us the sum we need to find in the remaining path. We then recursively call hasPathSum for the left and right child nodes, passing the updated remaining sum to each call. The method will return true if either subtree has a valid path sum. By using the logical OR operator, we ensure that only one valid path is needed to satisfy the condition. This recursive approach continues until either a valid path is found or all possible paths are evaluated, making it a concise and efficient way to solve the problem. Here, we start with a simple example to better understand the solution. The target sum is 22, and we begin at the root node, which has a value of 5. Subtracting 5 from the target sum leaves us with 17, which is the remaining sum we need to find along the path. Next, we move to the left child node with a value of 4. Reducing 4 from the remaining sum gives us 13. From there, we continue to the left child node with a value of 11. Subtracting 11 leaves us with 2. Now, we explore the left child of this node, which is 7. Since this is a leaf node and its value does not match the remaining target sum of 2, we return false for this branch of the path. Next, we check the right child of node 11, which has a value of 2. This is also a leaf node, but in this case, its value matches the remaining target sum of 2. As a result, we return true for this path. This true value propagates back up the recursion stack, ultimately confirming that a valid path does exist. The result for this example is true since we successfully found a path that sums to the target value. Now, consider a second example where the tree is much smaller, and the target sum is 5. Starting at the root node with a value of 1, we subtract 1 from the target sum, leaving 4. Moving to the left child node with a value of 2, we see that this is a leaf node, but its value does not match the remaining sum of 4. Therefore, we return false for this branch. We then move to the right child of the root, which has a value of 3. This is also a leaf node, and its value does not match the remaining target sum of 4. Since both the left and right subtrees return false, we conclude that there is no valid path in this tree that adds up to the target sum. The result for this example is false. Finally, consider the case where the tree is empty, and the target sum is 0. In such a scenario, there are no nodes to explore, so we immediately return false. The output for this example is also false, as there cannot be a valid path in an empty tree. The time complexity of the hasPathSum function is O(n), where n represents the total number of nodes in the binary tree. This is because the function uses a depth-first traversal, visiting each node exactly once. At each node, the function performs a constant amount of work, such as checking whether the node is a leaf and subtracting its value from the target sum. In terms of recursive calls, the worst-case scenario involves traversing the entire tree, meaning there will be n recursive calls in total for a tree with n nodes. This is why the total computation scales linearly with the number of nodes, resulting in O(n) time complexity. Now, in the best-case scenario, such as when the root node is null, the function exits immediately, requiring only O(1) time. For a balanced tree, the traversal might stop earlier if a valid path is found, but we still consider the worst-case scenario for big O analysis. In the case of a skew tree, where all nodes are arranged like a linked list, the function processes all n nodes, reinforcing the O(n) time complexity. The space complexity of the hasPathSum function is O(h), where h refers to the height of the binary tree. This is because the recursion relies on the call stack, and the maximum depth of the recursion corresponds to the height of the tree. For a balanced binary tree, the height is approximately log n, which means the space complexity in such cases is O log n. However, in a skew tree where all nodes have only one child, the height becomes equal to the total number of nodes, n, leading to an O(n) space complexity. It's worth noting that each recursive call only uses a constant amount of space for its local variables, but since the recursion depth is directly tied to the height of the tree, the overall space complexity depends on h. This means the memory required grows with the height of the tree, highlighting the importance of considering tree structure in analyzing space usage. A brute force approach to solving this problem would involve generating all possible paths from the root to leaf nodes and summing their values to check if any of them match the target sum. This would result in a time complexity of O(2 to the power of h) in the worst case, as there are 2 to the power of h potential paths in a binary tree of height h. The space complexity, however, would still be O(h), since the recursion depth is determined by the tree's height. In comparison, the current solution is significantly more efficient because it avoids generating all paths explicitly. Instead, it performs a direct traversal of the tree, ensuring that each node is visited only once. This optimized approach achieves a time complexity of O(n), as the traversal scales linearly with the number of nodes. The space complexity remains O(h), as it is still determined by the height of the tree due to the recursive call stack. This balance between time and space efficiency makes the current solution optimal, especially for balanced trees where the logarithmic space complexity offers a clear advantage over naive methods. Here are some common mistakes to watch out for while solving the pathsum problem. First, a frequent error is confusing the base case with leaf nodes. It's essential to check whether the current node is a leaf, meaning both its left and right children are null, before verifying the path sum. If you skip this step, you might incorrectly sum paths that terminate too early. Next, be careful not to modify the target sum directly during recursion. Subtracting the node's value from the target sum without restoring it after returning can corrupt the sum for sibling recursive calls, leading to incorrect results. Another mistake is not handling null nodes properly. If you try to access properties of a null node, such as root.left or root.right, without checking if the node is null, it can cause runtime errors, especially in edge cases like an empty tree. Finally, inefficient path reconstruction is another pitfall. Instead of explicitly constructing the path at every recursive step, focus on tracking the sum only. Constructing paths unnecessarily increases both memory usage and runtime complexity, which can slow down your solution significantly. Overcomplicating iterative solutions is another challenge to avoid. When using a stack-based iterative approach, make sure you handle both the node values and their running sums clearly. Writing overly complex code here can make debugging difficult and increase the likelihood of logical errors. From an interview perspective, it's important to discuss trade-offs if asked. For example, recursive solutions are simpler and easier to write, but iterative approaches give you better control over the stack size, which is valuable for very deep trees. It's also crucial to test for edge cases. Be ready to handle scenarios like an empty tree, a single node tree, or trees with negative values. Additionally, always highlight time and space complexity in your explanation. For this problem, the time complexity is O(n), where n is the number of nodes, and the space complexity is O(h), where h is the height of the tree, due to the recursion stack. Lastly, understanding tree traversal patterns is key. This problem relies on a depth-first search or DFS approach, which can be extended to solve many similar tree-related problems. If you'd like to explore related problems, there are several variations that build on the pathsum problem. For instance, LeetCode 113, pathsum 2, asks you to find all root-to-leaf paths where the sum equals the target. In LeetCode 437, pathsum 3, you need to count the number of paths that sum to a given value, but these paths don't have to start at the root. LeetCode 129, sum root-to-leaf numbers, focuses on calculating the sum of all numbers formed by root-to-leaf paths, while LeetCode 257, binary tree paths, requires you to return all root-to-leaf paths as strings. When it comes to alternative approaches, the recursive DFS method is the standard. Here, you subtract the current node's value from the target sum and recursively check the left and right subtrees. This approach is simple and intuitive but does use O(h) space for the recursion stack. Alternatively, you can use an iterative DFS approach with a stack. In this method, you simulate recursion by pushing both nodes and their running sums onto the stack. This avoids recursion stack overflow but requires careful bookkeeping to track state correctly. Another alternative is breadth-first search, or BFS. In this approach, you use a queue to explore all nodes at the current level before moving deeper into the tree. By tracking cumulative sums as you go, you can verify the path sum at each step. However, BFS is less commonly used for this problem. One reason is that it may require significantly more memory, especially for wide trees where the number of nodes at each level grows quickly. Still, it's a valuable approach to know, as it might be more suitable in scenarios where you need to prioritize level order processing over depth-first traversal. Great job working through problem number 112, path sum. To summarize, we discussed how to use depth-first search to solve the problem efficiently, reviewed time and space complexities, and highlighted key takeaways. Be sure to practice similar problems to solidify your understanding. Thanks for watching, and see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!